is just some examples of doing Fitch proofs in the Logica interface on the Stanford website. So I got 3 problems, which I think are kind of subjectively ranked by me as easy, medium, and hard. None of these are really obscure ones, but I wanted to show several different examples of like the basic proof techniques in Fitch. So using and elimination, using or elimination, and using negation introduction. Maybe later on I might do another one doing some and introduction as well as or introduction, although that's pretty simple. And in a later video I'll do quantifiers. So start with the easy one. So we just add in some P, Q, and R as our object constants. Now I don't even think you need to do that, but I just did it just so we have them sort of loaded up as things we can refer to. And we want to know that if I assume this thing, so the important thing to read this is the main connective is the arrow here. So if we're just looking at this conjunction, P implies Q and Q implies R, if both these things are true, then P implies R is true. So in Fitch, whenever you want to establish the truth of an arrow, you always start with an assumption, and we just put in our assumption, so P arrow Q and Q arrow R. And I believe that is the, oops, syntax error. How do they like it? Oh, they like equals. Everybody's a critic. All right, so we're going to assume that. Now, some people might take that as premise. That's fine, and basically equivalent, So we want to know that we can, after a bunch of work, print the arrow P implies R down at the bottom, right? That's our goal. And in order to print P implies R down at the bottom, we're going to actually have to make another assumption. So we're going to actually assume P, because our goal is to print the implication P implies R. So we hope that within this sub-sub proof we can get to R. Hide that. All right, now if I want, I can do and elimination on this, I believe, although maybe I need to reiterate it into line 3. Let's see. Nope. Nice. So the good news is that life becomes considerably easier now. I have P to work with, and I have P implies Q, and P implies Q, that is what we have implication elimination for, and that allows us to print Q. And then Q and Q implies R, it's another example of implication elimination, because I want to get rid of that arrow to get at the thing on the right. And now from P, I have gotten down to R, which is exactly the statement P implies R. To print a statement P implies R, I just close up the assumption that I started on line 2, and I do that with implication introduction. So I do that. And now if you look, I had 2 assumptions, and one was really the hypothesis, or some people might call it the premise of the argument, P implies Q and Q implies R. I want to show that that implies P implies R, and I've arrived at that on line 7 after assuming the hypothesis on line 1. So I'm just going to hit implication introduction again, and that's the proof. You can see that it's just written in the sort of and instead of wedge format that this program uses. All right, so that's a pretty easy one, and there wasn't really much going on here. The basics were and elimination, so breaking apart the conjunction, and implication elimination. And those are 2 pretty easy rules to use, but they're bread and butter, so good to know. Also, the more basic framework of how to prove an implication. Let's do another one of these. Let's do the medium. And again, if you think that these are trivial, or if one seems easier to you, this is just totally subjective. So let's start by assuming the thing that we want to assume, P or Q. You always use a pipe operator in Fitch for an or statement, and P arrow Q, and we want to close this up by printing some ways down just Q. This is a little different. And if you think about it a little bit kind of in ordinary language, what it's saying is, suppose that P or Q is true, and we know that if P is true, then Q is true. Well, in the first case, if Q is true, we're done. We know that Q is true. In the other case, if P is true, then we can feed it into P implies Q and get that Q is true, right? And that's kind of the basis for something called OR elimination. So what we're going to need is this OR statement by itself, and we're going to need to show that P implies Q and Q implies Q. Now, this is provided for us by breaking it apart. So this is going to stay put. We need to show that P implies Q and Q implies Q. Well, one of these is already provided for us as a hypothesis, right? The other one, we need to show Q implies Q. That's really easy because if Q is true, then Q is true. So let's show that. I want to print an arrow, so I assume Q. And I don't even need to reiterate. Some people would click for and reiterate it, but you can just print this, and that'll give you the arrow you want. And now this is an important thing, is that if you have P or Q and they both imply Q, OR elimination allows you to just print the thing on the right-hand side. Cool. And now we have one more assumption to discharge, which is on line 1, and that is going to give us our implication that we're looking for. Nice. So that's one. And maybe you might say that that's easier or as easy as the first one. The main thing is that OR elimination can be a little subtle, and maybe we'll do some more examples of that down the line. I think that besides negation introduction, OR elimination can be kind of sneaky and can give people trouble. So let's do one more. So now here we have P and Q, and we're not given an implication here. We're given just a flat statement, and it's an OR statement. This is, sometimes it's like you're looking for a handhold, a place to start on these problems. And for this one, I would say that if you don't have a real clear picture of how to attack, try to assume the negative and derive a contradiction. That is, let's assume that this is false, and we will derive a contradiction, right? So in order to do that, you assume that this statement is false. So, P arrow Q. And we want to show that we can derive contradictory conclusions from this assumption, right? So this is, we want to show that somehow this leads to, by assuming this, we can derive maybe something like a statement C, as well as if we assume it again, we can just derive the statement not C. And that allows us to use negation introduction, which is probably the most powerful of the tools, but it takes a little work to get to. So, we think in sort of the meta logic, not just within the Fitch syntax, but kind of in common language. If this is false, what do we know about P? Well, P has to be false, right? But if P is false, then we can show that P implies Q is true, right? Because of material implication. And then P or P implies Q would be true, right? So that's basically what we're going to show, is that we're going to show that if this is true, then actually P or P implies Q is true. And then we can also just say if this is true, then itself is true. And those will be contradictory things. That sounds a little weird at first. Let's just see where we get. All right, so first, let's show that under the assumption on line 1, P must be false, all right? We're going to be doing a lot of negation introduction, and so whenever you want to put a negation in front of something, you begin by assuming it, and you derive contradictory conclusions, right? So we're assuming that P is true, and we want to get a contradiction. Well, obvious contradiction is, let's contradict this. This statement is actually weaker than this. If I know P is true, I automatically get that this is true, and that's called OR introduction. And we just do, there we go. And Fitch always obliges us with both versions. But this shows that P implies P or P implies Q, right? And so now we can do that. And now we can also assume P, and we can show that it implies a negative. We don't actually derive it from P, we just reiterate the assumption on line 1. You're always allowed to reiterate things that are higher up in the hierarchy of assumptions and subproofs. And we get an implication introduction. And now this shows that under the assumption on line 1, if P is true, then two contradictory things must happen. P or P implies Q, as well as its negation. And anytime you have that, you can do a negation introduction, right? So we know that under the assumption on line 1 that P is false, right? Now let's show that P implies Q is true, right? This is going to look a little weird, but we're going to prove that if P is false, then P implies Q is true, right? Now, if to establish that P implies Q, you actually assume P, right? And this looks crazy because we have here not P on line 8 and P on line 9, which are clearly contradictory things, right? This is actually really good because now we have contradictory things. We can print whatever we want. What we want to do is show that we can derive Q from these assumptions, right? Because then assuming P, we can derive Q. And in order to do that, we have to work very roundabout and show that not Q is false. So in order to establish Q as a consequence here, we're going to assume not Q and show that it is false. All right, this sounds a little weird, but let's see where it gets us. So let's assume this. And the good news is that the negation introduction here is really quite simple because I have two statements, not P and P, above it in the hierarchy, so I can just reiterate, and they will clearly give me a basis that I can use to get a negation introduction on not Q. So I can say if not Q, then certainly I can reiterate line 8 down here and get this. Let's assume it again, and now I can reiterate this, get this down here, get another one going. Now I show that not Q implies P and not P. You see that there was nothing special about the statement not Q. I could have printed anything I wanted here, right? And that's because I'm operating under contradictory assumptions. You can print whatever you like. That's just a feature of logic. And now I have negation introduction because I have not Q implying two contradictory ends, so not Q must be false. I get not Q, and now I'm going to just eliminate that double not. And now I showed that, if you look at the assumptions, it's like I opened it with P, closed the sub-assumption, closed the sub-assumption, and so now when I close this, I'll get P implies Q, right? So from not P, I was able to derive P implies Q, and now how is that going to give me a contradiction to the assumption on line 1? Well, I can always OR P implies Q together with P, right? And that's going to give me a clear violation of the assumption on line 1. Although Fitch really makes us do if this were a more simple system, we would be able to just call it a day. Deriving this, we get this, therefore this must be false. Fitch makes us jump through a little bit more hoops. We have to do negation introduction. So first we close this up. We show that if if it is false that P or P implies Q, then it is true that P or P implies Q, which sounds ridiculous. And now let's take this as our assumption again, because for a negation introduction, you need that. And now I am just going to print itself as its consequence, because that's the negation of what I have over here. And so I'll do this. And now to get my negation introduction, I do that. And now I have my negation implication. And so this is the conclusion. It's not within the scope of any assumption. And that gives